I would like to introduce Virgil Ganescu from the York College of Pennsylvania, presenting Enhancing Learner Ownership and Competence, the Relevance of Differential Equations in STEM Academic Curricula.
Thank you, Anna. Welcome, everybody. Happy Valentine's Day, if and as applicable. I will go ahead and share my screen right now. And I think you should see the slides. Do you see them?
Yes.
Okay, fantastic. All right, so I would like to walk you through the timeline of a multimodal, multi-level observational study that I have conducted over the past three, going on to 4 years in in a 200 level ordinary differential equations course at a 4 year college. So with that said, feel free to interrupt me at any given point in time. I would like to make this as collegial and informal and mutually beneficial presentation as possible. Okay, so increasing student ownership, differential equations in STEM education. As an engineer, I have had the opportunity uh, to take many classes where the hands-on component actually reinforce the fact that once you do things yourself, you become more vested. From that, moving on to professional career in engineering, I realized that once we pick up the pieces and run with the pieces, we become even more vested in what's going on. Needless to say that in a professional environment, you have accountability, responsibility, and all the other facets that perhaps in undergraduate education are in an embryonic stage. Okay, so with that said, um, we'll go over observations made early in the semester, going through student development strategies, data collection, and ultimately the outcome. Um, not knowing where the audience is coming from, I would like to reinforce a couple of things surrounding differential equations. I prefer to tell my students that algebra is boring, calculus is for babies. I'm exaggerating, of course, and that's not what I'm telling them. But um, the point that I'm trying to make with my students is that differential equations is the one course that has the potential to take us even closer to real applications. In calculus, we do touch on real applications a little bit, but for the most part, we set the foundation for what's going to happen after ordinary differential equations and partials. So applications that we touch on span anywhere from science, engineering, and the traditional STEM fields. Um, Another aspect that I reinforce day in and day out consists of the critical thinking development and analytical thinking skills. And I'm beyond confident that we all know that for the most part, once the course is over, most students will lose contact with the concept matter unless they're math majors, unless they solve differential equations day in and day out, etc., etc., etc. However, for the most part, it's one and done, or two, depending whether or not they continue their education. All right. So again, bringing relevance to mathematics in the context, obviously, to me is part of the foundation. Okay. Now, again, as we all know, there will always be students who just simply want to check the box, do the bare minimum, get their 3.0 or whatever the case may be, and carry on. All right. Now, at our institution, the main flavor at your college, four-year college, the main flavor is, let's just say, quote unquote, liberal arts. Of course, we have engineering majors, math education, math majors, etc. However, for the most part, we have liberal arts. So, over the past many years, I have had the opportunity to facilitate, like I said, 200 level ordinary differential equations, 1 semester long course, 4 credits for engineering students, biology, physics, and economics, and a few math education and math majors. Now, in terms of the practical applications, uh, even though it's a 4 credits course, the nature of the course is purely theoretical. There are 3 of us facilitating this course in the average semester, and we all are trying to, in an effort to meet the learning outcomes, to give it a certain spin in such a way that we meet the learning outcomes and we engage the students slightly beyond the walls of the classroom. All right, so hands-on. These are personal observations that I have had the opportunity to gather by contrasting I call it pseudo flipped classroom environment, which I do for the most part. I expect the students to watch certain audio, video, multimedia materials that I have created. Before class, I preview the theoretical notions during the first half of the class, and the second half of the class period, I have students work in groups and or individually to reinforce the topics scheduled for a respective day. Okay, now, okay, and now the goals are multifaceted. One, um, what are we trying to accomplish? So I'm trying to get the students to understand that it's not how we solve a linear equation. For instance, yesterday we have covered exact equations. That's great. Go through the process, solve them, check your answer, life is good. But at the end of the day, what are the applicabilities of these equations? What context can we find them on? What's the next step? You know, if I become fond of exact equations in the context, what more can I do with them besides just solve an equation and be happy that I got 100% in a homework or whatever the case may be? So I'm trying to highlight the relevance in what's going to happen next in their future educational as well as professional endeavors. Okay, so again, let me say it one more time. So I have contrasted the observations made in my pseudo flipped classroom environment with observations that I have gathered teaching a traditional uh, 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 in a traditional format. So I stand up, I talk for like 100 minutes, and so on. So early in the semester, now I typically am doing my best to structure the course in a project-based type of a format. So therefore, I begin the course with a minimum of 6 planned projects. Okay, real life in the beginning, very, very simplistic. Newton's law of cooling, population modeling, and so on. Now, I have noticed that data collection, the simple fact that students collect some data, adds a lot of weight to this teaching and learning process. Students who actually collect the data versus getting the data from the internet, collecting the population of the bears in South Central Pennsylvania or whatever the case may be, they seem to become a little more vested and more interested in how we go about doing whatever it is the framework of respective project, linear equations or simple equation with separable variables. Okay. Now, in the beginning, I suggest a series of topics. Needless to say that most students in week 2 of the semester, they tend to mirror the topics that I suggested. Okay, so early on is like monkey see, monkey does. I'm not using the quote and I'm not calling them monkeys, but that's how things develop. Again, mind you, this is undergraduate. Most of them are non-math majors, but they are engineering, math-minded majors, for lack of a better term. Okay, so early in the semester. Now, throughout the second part of each of the class sessions, um, I have been able to the average class size has ranged between 20 and 30 students. Now, this is a 4 credits course, and we meet for 100 minutes twice a week. Okay, so about 50 minutes, I talk about the theoretical notions, and the remaining 50 minutes, we're talking about they are talking, they're working in groups or individually on the topics at hand. Now, given the relatively small class size, I have had the opportunity to take a differentiated instruction approach when where I'm tackling group A with topic X, whatever that topic may be, to reinforce the foundation, the framework that they may be struggling with. Now, on top of that, we have used ChatGPT as well as Microsoft Copilot to to gather feedback from various prompts. Now, these prompts, this has been a time-consuming part for me. You know, if you ask ChatGPT, okay, linear ODEs, you're going to get as broad of a range of possible examples or paths that's not even funny. So therefore, this has taken some time, some preparation time for me prior to the class sessions. Do I make sense? Are you guys following?
Yes.
All right, that's cool. Typically, I check on the eye contact and subliminal messages sent by the body language, but I cannot see that right now. So anyway, so I'm using the AI prompts to, for instance, tackle whatever foundation gap that we may have with group one versus, oh, that went back a little bit. Let me go back. Okay, so I'm using AI prompts to reinforce certain concepts, certain holes that the groups or the individuals may have while working on the topic at hand, the topic that we tackle at that moment. Now, as I'm already mentioned, so everything while we do talk about and of course cover every single one of the tools that one and concepts that one would cover in the traditional ordinary differential equations course, I'm trying to take a project-based package to things. Okay, so as I said earlier, about 6 projects starting in the semester, and depending how every class is the same, but every class is different. So depending on the speed at which we tackle the semester and we progress to the semester, I may deviate from the 6, never in the negative direction. So always add 1 or 2. Okay. So what have I found? Now, I have looked at qualitative as well as quantitative data just from my own classes. I did not have any other controls. I did not look horizontally among compared with my colleagues or anything else. I looked at student feedback as well as your traditional grade distribution. I have noticed that those students who go beyond the suggested project themes, topics that I recommend, tend to become more vested um, in the topics at hand, whatever it is that we cover. At the same time, there was a direct correlation between their grades and the level of involvement in said projects. Okay, and ultimately, you know, you meet with students in the office during office hours. You spend time with students before class, after class, and so on. But I have noticed that students who harass me before class and after class happen to be those students who are actually more vested in the data collection, in the project that they were involved with, and so on. Okay. Now, moving forward in my delusional reality, I would like to actually start with some classes, smaller classes. If I will have the opportunity to have even smaller than 20, with smaller classes, I would like to continue on a path of actually not necessarily only collecting data, but building some prototypes. Very, very simplistic. Nobody wants to colonize Mars tomorrow after taking an ordinary differential equations class. But I would like to also sprinkle student initiated projects, whatever those projects may be. Of course, there's need for evaluation. Make sure that when the rubber meets the road, we can accomplish all of these phenomenal goals within the scope, timeline, and all of that of the course. Okay, and ultimately, even emphasize even more the interdisciplinary relevance and the impact on whatever topics they may run into in business, risk management, economics, and so on. Now, the only limitations that, well, I shouldn't say the only, the limitations that come to mind surround um, the logistic aspects. I mean, 20 students, if I don't combine them in groups, I don't have enough time to actually take this differentiated instruction approach, project based, and all of that, because it takes a lot of work to set the foundation, the expectations, do the I shouldn't say convincing work, make sure we're all on the same wavelength, and then get to work and gather the results. Okay. Now, towards the end of mid-semester, end of the semester, I'd say those more vested students have taken upon themselves to collect data themselves from whatever their interests are. So what I have on the screen right now, I have just many different topics. A simple example of a student who actually said, you know what, I can gather temperature data points from my, I believe it was a Subaru that had some thermostat issues or whatever the case may have been. And it turned out that his project was actually great. And you know, when we collect the data, we are able to paint the picture of the real phenomenon going on. And oftentimes, the data that we collect also tends to reveal future possible trends. So in this case, there was a combination between the two, and the person noticed that something was wrong with the cooling system in that case. However, the data collection gave him such an increased interest, and there are many more examples like this. Such an increased interest in the course itself that I'm like, whoa, I'm sure it's not because of me, it's because of the student. Okay. Now, on top of that, two more example projects um, along the lines of pushing, exploring uh, uh, the topics outside the classroom walls. One dealt with, I believe, reduced lunches. The second one, student A, which, you know, there are many suggested scenarios on the internet, on Semiotic website, and virtually everywhere. Um, some are traditional examples that we all use in our classroom environment, but some are like, whoa, I would never have thought about anything like this. And the second example is a student who actually collected data at her place where she conducted the co-op. Mandatory experiential education in one of the engineering programs. We good? Can I progress to the next slide? Can you all still hear me?
Yes, we can.
All right. So that's that. So what they did, and you know, I wish I would have time to share with you the outcomes that I have gathered through the semester, the write-ups. You know, in week 3, they turned something in. It was like, whoa, there's gonna be a lot of work to do with these kids. And then those who actually bought into the topics, bought into what needed to be to happen, and everything else, and they were able to take things beyond what we covered in the class, produced excellent results. Okay, so on the left you have the reduced lunches example. I don't remember. Oh yeah, I believe the student used some higher order numerical methods to contrast what they obtained analytically with the results yielded by what is it, Rangekara, if I remember correctly. And on the right side, that was the cooling data for some engine in a Harley Davidson motorcycle that the student worked on during their co-op at the local plant. Okay. So looking forward, again, I will continue to emphasize the fact that ODEs are foundational for STEM fields. Um, in my mind, I would like to see a partial differential equations course added to engineering, at least at our institution. Um, I have noticed that if we're using AI enhanced as well as project-based learning, the understanding and interest in the topics, um, I can say has skyrocketed, but has increased exponentially. And I'll share with you in just a second another tangible outcome. And if we continue to link the real world applications with whatever it is that happens in the classroom, in such an example, ordinary differential equations, um, going beyond the mechanics of how we do something, I think the students will amaze us with what they can do and they're willing to do. Now, personal observation. So over the past 3 years, I have facilitated close to more than a dozen ODE courses, full semester ODE courses, and I can tell you that about 80% of those who who showed vested interest in this class, the projects, and everything else, actually ended up declaring a math minor at our institution. So there's a combination of factors. One of those factors consisting of the fact that for a math minor, as an example, a mechanical engineering major from your college would only have to add 2 math courses. So that's highly doable. No major time constraints or anything else. But I think this course was a stepping stone towards that decision. Okay, so that's all I had.